Welcome back to Algebra 2, Topic 35, Graph Logarithmic Functions. So this is a three-part video. We're going to start off with part 1. So, graphing logarithmic functions. We're going to first identify the key features of logarithmic functions. Now this is very similar to the key features of exponential functions, so you might, these terms might sound familiar to you. So first what we want to note is that logarithmic functions are inverses of exponential functions. So if we were asked to graph y equals log base 2 of x, what we're first going to do is create a table of values for the exponential form of the logarithmic function. So if we have log base 2 of x, if we wanted to convert this to an exponential form, since 2 is our base, and then we're going to have our exponent there. So if we wanted to plug in our x values into our table, into our function, in order to determine what our y values are, we can do this by just going to Desmos. So we'll open up Desmos. So our first one was 2 to the x, and our first x value is negative 2. So 2 raised to the negative 2 power gives us 0.25, so 1/4. Our next one was 2 to the negative first, so that is 1/2. Then we had 2 to the 0, gets us 1. 2 to the first gets us 2, 2 squared gets us 4, etc., etc. So we're going to go back to our PowerPoint and fill that in. So when we had 2 to the negative second, that was the same thing as 0.25. 2 to the negative first was 0.5. 2 to the 0 was 1. 2 to the first was 2. 2 squared was 4, etc., etc. Now, in order to graph the logarithmic form of this function, we're going to interchange the corresponding x and y values. So basically what we're just going to do here is swap them. These ordered pairs will then represent the logarithmic form of the function. So instead of writing negative 2, negative 1, 0, 1, and 2 in our table right here, we're going to write the y values. And those are going to become our new x values. And when you deal with inverses, all you're doing is flipping x and y. So here that will give us the graph of log base 2 of x. Then, since we have those points, we're actually going to graph the ordered pairs. So we had over 0.25 down negative 2, over 1/2 down negative 1, over 1 up 0, over 2 up 1, over 4 up 2, etc., etc. So we can see our graph is going to look something like this. Now we're going to identify the key features. So looking here, our domain is all of our x values. So notice how we don't have any negative x values. We're just going to stop at 0. But since it never fully hits 0, it's only approaching 0, that's why we're going to have a parentheses here. And it keeps going on forever and ever and ever until positive infinity. Our range is all of our y values. So here, this is pretty standard. We're just going from negative infinity to positive infinity. It's going all the way down, and if we were to zoom out, it would go all the way up. Now notice here how we're talking about the x-intercept. We're so used to seeing the y-intercept, but we actually don't have a y-intercept, and we'll see that in one moment. We do have an x-intercept right there. Kind of got off my graph, but so that x-intercept is at 1. And we have an asymptote. So the asymptote is why our domain is never going to negative infinity. It's approaching 0, or it's approaching the y-axis. So our asymptote here is the y-axis, and if we were to write that in equation, we would get x equals 0. Remember, x equals is for vertical lines. Our end behavior, we're going to take into consideration what we had down for the domain and range, and that's going to help us with our end behavior. So as x approaches 0, because remember x doesn't go to negative infinity, because we have that asymptote there, y goes to negative infinity. Y keeps going down, 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 down. Or as x goes to positive infinity, y also goes to positive infinity. So that's graphing a logarithmic function. Now, we've mentioned before in the topic before that there are things called a common log, so that's where there's a base 10. So just so we have this summary here, we're going to compare the logarithmic form and the exponential form of the graph for the common log, where we have a base 10. So these functions are inverses, as we've noticed before. So their graphs are actually, if we were to look at the logarithmic form and the exponential form, their graphs are reflections. Across the line with this equation, and this line right here. That line is y equals x. So that is the line of reflection that we see from the exponential form to the logarithmic form. So if we were to compare these two with all those key features, if we have y equals log base 10 of x, remember we don't always write the 10 there, it's just kind of assumed. If we look at that, our domain is 0 to positive infinity, because it never goes negative. Our range is negative infinity to positive infinity. Our x-intercept is at 1 right there. Our asymptote is still at the y-axis. So when x equals 0, if we see that right there. And for our end behavior, as x goes to 0, y goes to negative infinity, and as x goes to positive infinity, y goes to positive infinity. Now, if we were to look at the exponential graph, y equals 10 to the x, the domain here, we had all of those x values, so it's negative infinity to positive infinity. And again, I'm looking at this red graph here at the top left. Our range, notice how our range never goes negative, never goes below that x-axis. So our range is from 0 to positive infinity. We do have a y-intercept right here. So our y-intercept is at 1. We also have an asymptote here. This asymptote, let me do a different color. This asymptote is at the x-axis as opposed to the y-axis, where y equals 0. And our end behavior is as x goes to negative infinity, y goes to 0, as x goes to positive infinity, y goes to positive infinity. And that is graphing the logarithmic functions.